Now we will compute a double integral by using a different frame of coordinates, and in particular we will switch to the polar coordinate system. Sometimes problems are described in a system of coordinates which is Cartesian. We have an x-axis and a y-axis, but some other times it is more convenient to work with a different frame of coordinate. For instance, we can use a radial coordinate, which is r, and then an angular coordinate, which is theta. And this can be very helpful in those problems where there is some kind of symmetry. For instance, r and theta are connected to the x and y axis if we work it out, because the x coordinate is just r cosine theta, whereas the y coordinate is just r sine theta. So we have this relation between the x and y coordinates to the r and theta coordinate. If you work it out, you can also express r and theta in terms of x and y. But we will not need it here. We just need this sort of relation. We will apply this coordinate system to the computation of the area of a circle. This is a simple application that we already studied when we computed the area of a circle by using a double integral, and we did so in Cartesian coordinates. But we will see that by using polar coordinates it can be much simpler, because of the symmetry of the circle. And theta is a parameter which ranges from 0 to 2 pi, as you can imagine, because as we move from 0 to 2 pi, r describes a circle if it remains constant. If we move theta and keep r a constant, r describes a circle. Whereas if r changes, r can describe any trajectory. In particular, it can describe the entire x and y plane. We will see that this sort of description is much easier to adopt when we have these sort of symmetries. We have some portions of circumferences or other types of symmetry around the origin. In 3 dimensions there's spherical coordinates, that's also very useful. We can see something of that as well. There's also cylindrical coordinates. There are other types of coordinate systems which can be very useful. This is a circumference. We need to compute the area inside this circumference, so that's a circle. This is just a double integral of this domain that I will call A over dx dy. If we switch to a different set of coordinates, this becomes equal to integral over another region. In general, it will be a region A prime, but instead in here we have to insert the Jacobian of the variable x and y with respect to the variable r and theta, in this case, dr d theta, or d theta dr, depends on which kind of integration we are going to perform first. So let's compute the Jacobian. We need to compute the Jacobian. It's not so difficult. The Jacobian is just dx over dr, dx over d theta, dy over dr, dy over d theta. In general, we should also consider the fact that these are areas, right? So we need to consider also an absolute value. This is the absolute value of the determinant, not just the determinant itself. An area in one frame to another, the sign of the area should remain the same. So it makes sense to put the absolute value here as well. R is positive. In case we get a minus r, we should replace minus r by plus r in that case. Let's see. This becomes equal to, okay, let's take the determinant. Okay, the derivatives are dx over dr. dx over dr is just cosine theta, because we keep theta constant and vary r, and that's the derivative. It's the constant itself, it's cosine theta. And then we have dx over d theta, which becomes equal to minus r sine theta, because we have to differentiate cosine theta. R we treat as a constant. dy over dr is just sine theta, whereas dy over d theta is just r cosine theta. And we take the determinant and then take the absolute value if needed. Okay, we get cosine theta times r cosine theta, it's r cosine squared theta. And then we have minus, so it's plus r times sine squared theta, plus r sine squared theta. And this is equal to r times cosine squared theta plus sine squared theta, but cosine squared plus sine squared, it's obviously equal to 1. That's a very simple trigonometric identity. So we get r. We don't need to take the absolute value. Our Jacobian depends on r. So it's a constant in theta. It doesn't depend on theta, but it varies along r. So our integral becomes the double integral, and then we need to insert the domain here, the region of integration, but we will see that in a moment. We have r. Let's first integrate over r and then over theta. r d theta. And this is something actually easy to see. Even if we don't know anything about Jacobians, we can still infer that in polar coordinates we should integrate areas like this. Why? Because let's take a frame of reference. Here's x, here's y. Let's take r. This is r. This is theta. Let's take r plus dr. Let's take an infinitesimal quantity r plus dr. This is still r, but this is d theta. Let's vary theta first. This is d theta, and this is still r. This is the amount dr, if you want. Dr here and dr here. Okay. So a very small region in the r theta coordinate system. So in the polar coordinate system, an area is described by this sort of rectangle. This shouldn't be a rectangle because this portion here is not a line. This is a piece of a circumference. But when we consider infinitesimal quantities, this can be considered simply a line. So the area of this rectangle is just this side times this one. So what is this side? This side is just dr. Whereas this side is just the length of the radius of the circumference that I didn't draw here, but it's the circumference with radius r times the variation d theta, the angle, because r d theta gives me this. So the area of this portion in the polar coordinate system is just r dr d theta. Or maybe I should rewrite it as r d theta dr, where r d theta is this side, whereas dr is this one. So this is the way that areas are computed in polar coordinates. So that's why the Jacobian gives r, because r dr d theta is the same as r d theta dr. Okay, so this is the geometric intuition behind this. Some other times it is more difficult to interpret geometrically and intuitively this transformation. So in polar coordinates it's very simple, and this is why we are considering this example, because it's very simple and you get the idea. Let's now talk about the boundaries here. As you can see, our region is this one in the xy plane, but it remains the same in the polar coordinate system. And in particular, r starts from the origin and it moves all the way to r, the radius of the circumference. So we should integrate from 0 to r. Whereas theta varies all the way from 0 to 2 pi. So as r moves from 0 to r, theta takes r from 0 to 2 pi so that we can describe the entire circle. So we just integrate from 0 to 2 pi. The first integration gives us r squared over 2, the integration over r, because the derivative of r squared over 2 is 2r divided by 2, which is r. So it's integration 0 to 2 pi, r squared over 2, and we evaluate it between 0 and r, and then integrate over theta. But this thing is just a constant over theta. So the integration of theta is just the integration of 1, which is theta. So in here we get, if you want, r squared over 2 from 0 to r times theta evaluated between 0 and 2 pi. But the first thing here gives us r squared over 2, and the second evaluation gives us 2 pi. All in all, we get pi r squared, which is the result that we already knew.